Welcome everyone to our Rising Star Symposium series talk. So this talk we host from the Technical Committee on Cognitive Networks, TCCN. We are a special interest group in the AI and machine learning in security. So our chair is Professor Subha from Stevens Institute of Technology. I myself, Devashi Roy from UT Arlington, and Moinul is from George Mason. So we are a special interest group. So we have a LinkedIn presence, and the link is given here. So we have almost more than 600, almost 650 members right now. LinkedIn grow and we are growing. We are hosting this virtual seminar talk since 2021. Started from the time of the pandemic, and we had uh, virtual seminar series from various distinguished scientists and members, researchers. So this is the list of those talks, and these talks are available online from our website, also from the YouTube channel. So after that, we started to take in new initiative from the group, which is from last year, and our main initiative is to create a platform for the postdoc and senior PhD students, PhD candidates, to present their work to prepare themselves for job. So it's like an opportunity to have a mock job talk and to engage with broader audience. And we had held various talks from rising stars from various universities all over the world, and many of them had been placed in, had joined academia industry in one way or another. So these are our various rising stars from different universities, different part of the world. So today, overall, how we conduct our talks, we request everyone to be muted on the entry, and please stay muted throughout the talk. But if you have any question, please type in the chat box, and we will ask those questions at the end. So today our rising star is Dr. Sayanta Seth. He is a postdoctoral fellow from North Carolina State University. He received his PhD from Central Florida University of Central Florida in ECE department. His research interests include 6G, NextG, and beyond wireless communication, focusing on various areas of O-RAN, dynamic spectrum sharing, beam steering optimization, and all that. So Sayanta has many research awards and peer review, more than 10 peer review publications in the top venues, including transaction on communication, transaction on cognitive communication, and networking. So with that, I will stop. And Sayanta, thanks for coming here, and the floor is all yours.
Thank you. Let me start to share my screen. My screen visible?
Yes.
You can see the main slide window, right? Okay. All right. Hello, everyone. My name is Sayanta Seth, as Dr. Roy mentioned, and I am a postdoctoral research fellow at NC State University, and I work with Dr. Vijay Shah at NextG Wireless Lab. Among several research interests in wireless communications that I have, including millimeter wave communications, beam steering optimization. Recently, I have delved into digital twins, and today I'm going to cover some of my most recent research on predictive spectrum intelligence and digital twin-driven control for next generation of wireless networks. So let me start. Since most of beyond 5G, 6G, and the next G wireless communications rely on some sort of intelligence, AI or ML, it is very important that the radio access network that we are using is actually able to support such intelligence, and that brings us or that gives us the flexibility to host some intelligence inside the RAN itself, and that is made possible by Open RAN. So in the beginning of my talk, I'm going to talk a little bit about, give a little bit of background on Open RAN. And then I'm going to start talking about the spectrum coexistence problem that we have currently in the FR3 frequency band, that is between the 7 and 24 gigahertz band. Then I'm going to talk about recent research that I have done on digital twins to solve the spectrum coexistence and network control problem. And in order to do that, I'm going to present my first architecture that is what we called programmable open spectrum twin post architecture, where we directly leverage Open RAN to implement digital twins. And then within the post architecture, I'm going to talk about how predictive and policy-aware decisions are made, aligning to the ORAN standards. And then I'm going to talk about a simple test case that we developed to demonstrate the workability of our post architecture. Then I'm going to talk about a really novel problem that is also related to spectrum coexistence in the lower 12 gigahertz band. That is, how can fixed wireless access, FWA, coexist with the satellite incumbents in the lower 12 gigahertz band? We have proposed a tool called Ascent FWA to do some really needed performance evaluations in this 12 gigahertz band. And then I'm going to talk about digital twin assisted cognitive spectrum sharing for 6G coexistence, which is dubbed DigiCam. That is a study where we investigate the coexistence of 5G and beyond 5G cellular architecture in the presence of passive fixed satellite service FSS receivers in the 12 gigahertz band. So I go over the overview of our proposed DigiCam framework and a couple of algorithms or intelligent algorithms that we implement in this DigiCam framework. They're greedy and recursive deep reinforcement learning algorithms to control the macro base stations. And then we discuss some results. And finally, I'm going to talk about, again, a digital twin, but this time, instead of terrestrial, I am working on implementing or developing an end-to-end control loop that is a digital twin for the lunar surface. So if you don't know, NASA in its Artemis program is actually has already awarded Nokia as part of its tipping point program, where NASA is interested in investigating whether the current terrestrial 3GPP network that we have on the Earth can be directly taken over or ported to the lunar surface for various lunar missions. So that is something that I'm also working on, and I'm going to show some initial GUI, graphical user interface, of our digital twin that we have been developing for this NASA SBIR program that we won. So that is going to be my my talk for today. So let us start. So ORAN, a brief background, right? For decades now, when we talk about wireless cellular network, we mainly mean a monolithic architecture where the radio unit, the entire cell structure is created by a few companies. So there has historically been a very small set of companies like Ericsson, Nokia, and kind of companies like this that have been creating or making or manufacturing equipment or hardware for these cellular base stations. However, if you have something, if you have hardware that is made by a very small set of companies, then then we don't have, or then we are not able to introduce openness in this. And you can ask, why do we need openness? We need openness so that everybody, like from engineers to a radio resource, like from academia to engineers, everybody can contribute towards making this entire radio access network more intelligent, and we can create or write apps that can control various parameters of the cellular network. So ORAN is called Open RAN, and it is defined by ORAN Alliance. And its mission is to reshape the radio access network industry towards a more intelligent, open, virtualized, and interoperable mobile networks. So it was founded by these companies in 2018. And the most important or significant thing that ORAN brings to the table is the RAN intelligent controller. Okay, so the RAN intelligent controller actually allows the telecom operators to implement custom control logic, and that actually contributes to the intelligence of this entire radio access network. And also, through ORAN, we are able to disaggregate the monolithic the monolithic radio access network. When I say disaggregate, I mean, sorry. When I say disaggregate, I mean we are going to split this architecture into several different smaller architectures that can be made or created by different companies or vendors. And when you introduce openness, there are certain challenges that are introduced here. So the first challenge is the interoperability challenge. So if company A is creating the radio unit, and if company B is creating the distributed unit or DU, then obviously the two devices made by two different companies, they might not work as expected. So there is an entire study that we do to find out the interoperability issues and vulnerabilities for this openness. Although ORAN brings a lot of flexibility and intelligence, there is also another side of ORAN that need to be addressed that comes from this open architecture and security vulnerabilities. So in short, or the standard features of ORAN are network disaggregation. So the entire radio access network is disaggregated into smaller components, softwareization and virtualization. It has open interfaces, and there are certain RAN control services that can be leveraged for more efficient use of the radio access network. So when I say disaggregated radio access network, this looks kind of like this. So the front end, the RF front end, is called the ORU, that is the Open Radio Unit. And then we have the DU, that is the distributed unit, and then we have the CU, or the centralized unit. So these distributed unit can be simply a commercial off-the-shelf or CORS server that can run DU software. So there are various open softwares like SRS RAN DU, OAI DU that can be run that is there for free, and you can run it on your server. And then there are other companies that manufacture ORU, the radio unit that is the RF front end. For example, we work with Benetel ORU. We work with Vividian ORU. So as you can see, there are various companies that are going to manufacture various things. The ODU, that is what I said, that is the distributed unit. It can be any commercial of the shelf hardware from Dell or Lenovo, and it will be running free software. So there is this challenge of interoperability in ORAN that needs to be looked into. And then we have these two RICs, or RAN intelligent controller. So in short, they're called RIC, or RIC. So there is one RIC called the non-real-time RIC, and then the other one is the near real-time RIC. So the non-real-time RIC represents the non-real-time control layer that is operating at timescales greater than 1 second. And it hosts software that we called R apps. It hosts R apps which perform long-term operational optimization tasks, such as policy generation, model training, and network-wide analytics. And the non-real-time RIC communicates this control policies to the near real-time RIC through this open interface called A1 interface. Similarly, so this is a slow RIC, because it is actually it has a time scale of greater than 1 second. The near real-time RAN intelligent controller, the near real-time RIC, actually operates at time scales between 10 milliseconds and 1 second, and it hosts another set of software or applications called XApp, which perform fine-grained control actions, for example, scheduling, interference management, or mobility optimization. So this is what we have, and then we have the low-fi, the hi-fi, the MAC. The MAC is the block that is responsible for scheduling, resource allocation, HARC, and link optimization. Then we have the RLC, the radio link control, uh, which handles the segmentation, reassembly, and retransmissions, and so on. So in summary, this ORAN architecture disaggregates the radio access network, and it introduces programmable control points through the near real-time and non-real-time risks, and that makes it data-driven and digital to assistant spectrum control possible in real networks. Okay. Now I'm going to talk about the spectrum coexistence scenario in the FR3 band, 7 to 24 gigahertz. Why do we need FR3? So historically, we have been in the sub-6 gigahertz FR1 band, right? However, as time went on, until recently, like not recently, like 6 or 7 years, like we found that the sub-6 gigahertz bands is like completely congested, right? So then we thought of moving over to the FR2 band, which is 28 gigahertz and beyond, and that lies within the millimeter wave band. However, although it promised a huge bandwidth, the problem is that when you try to communicate in the millimeter wave band, there are certain physical aspects. For example, the links are not very stable. You have to be in the line of sight. If they are susceptible to blockage, rain, attenuation in the environment, and there are so many problems. However, there is a specific set of band that is between 7 and 24 gigahertz, which has been identified in the US National Spectrum Strategy as an opportunity, and it can be treated as a strategic mid-band. The incumbents that the services that are actually happening in this band are the LEO constellations. However, however, we can actually, with intelligent spectrum sharing strategies, we can also accommodate 5G, 6G, and other broadband in this band. So FR3 actually hosts sensitive incumbents, and they are the radio astronomy, RAS, Earth exploration and satellite services, EESS, and fixed satellite services, FSS. Now, the existing spectrum sharing models that we have so far, there are certain limitations that they are not really that much effective to do spectrum sharing in the FR3 bands, as they are very sensitive. These are all sensitive incumbents. So because they are so sensitive, the current spectrum sharing models are as they are basically database-based approaches relying on statistical propagation models, are not really suitable to do spectrum sharing in this FR3 band. Also, there are other methods like exclusion zone-based principle, which are actually overly conservative. It has been found that they're overly conservative, and by that I mean that you just put a threshold, and if the interference to noise ratio is crossing the threshold, then you just turn off certain base stations. So although it sounds good, but that is not really a good approach, just to have a static threshold, and I'm going to show why it is not. Current spectrum sharing models also have limited environmental awareness. Not all of them actually take into consideration how the environment is right now, whether it is raining or whether it is sunny. They don't take into consideration about that, and they are not designed for dynamic satellite mobility. Now, when we talking about digital twins, that is what I am working on for spectrum coexistence and network control. Digital twin, the concept of this is a high level conceptual diagram of a digital twin. So on the left, we have this physical world, the physical twin, where you can have any scenario. Since we are considering the FR3 band, right? So there is this radio telescope, then there is this LEO orbit where the LEO satellites. The LEO satellites have the inter-satellite links, and then the user terminal has this LEO uplink and LEO downlink, right? So this is the physical world, or the physical twin. And on the right-hand side, we have the digital twin, that is the replica of the physical world. And then you can have have certain modules or engines inside the digital twin, and you can have it based on your own needs. So there could be this is what we envision in our digital twin when we are talking about spectrum coexistence and network control in the FR3 band. So we can have the state prediction engine, we can have the channel estimation engine, we can have an error prediction and correction engine, we can have a resource control engine. So the state prediction engine is like basically predicting what is the next state going to be. So this is the physical world. So what is the purpose of the digital twin? It has to be predictive. Okay, if there is this satellite here at time t+1, where this satellite is going to be. So that is the state prediction engine. It predicts the satellite's trajectories, incumbents activity, how many users are there, how if at time t0 there are x users, at time t+1 how many users will be there. Then there is a channel estimation engine, and basically what we do is we can have two types of channel estimation engines. That is the 3D ray tracing. The classic example is NVIDIA's Siona that we use, which is computationally very expensive. Also, there could be model-based channel estimation where you use 3GPP path loss models or statistical models to model this to estimate the channel. However, channel in whatever way you create a channel, it is not perfect. So there will be errors in channel, right? So you can have intelligent algorithms that can do error prediction and correction within this in these channels that the channel estimation engine is producing. And then finally, you have the resource control engine that is basically controlling basically controlling the RAN resources, right? Like the transmit power of the base station, the beamforming directions, what is the scheduling for the users, and so on and so forth. However, it is a digital twin and this physical twin, they are in they're in synchronization with each other. So there is this feedback loop going on between the physical and the digital twins. So ORAN alone is not sufficient for spectrum coexistence. So spectrum coexistence is a specific problem that we are looking at, and ORAN is an architecture. So ORAN just gives us the framework. What you want to do with ORAN is up to you. So ORAN enables the control, but it does not predict interference outcomes. So control decisions are executed after the conditions are observed, not before outcomes are evaluated. And ORAN does not natively model cross interference or future spectrum impact. ORAN does not natively model this. You have to model this by designing appropriate RFs and XFs using your own algorithms to do this. So ORAN is an execution framework, and it is not a foresight engine. It cannot do spectrum coexistence problem all by itself. So spectrum coexistence is no longer really an option because spectrum is already densely populated or allocated across various types of devices and services, right? And we cannot expect exclusive access assumption. So this is not really possible in today's dynamic and multi-tier world, right? And static coexistence analysis is not sufficient for today's terrestrial and non-terrestrial systems. So to solve this, in order to look into this problem, I'll be talking about the first work, that is programmable open spectrum twin post for enhanced spectrum sharing in 6G bands. As I have been talking about, the problem is that there is a severe lack of predictive evaluation before the spectrum enforcement is done. Existing systems, for example, the TV white space, the TVWS, spectrum, CBRS SAS, ProSAS, zone management system, these systems, although they have certain strengths and they have certain weaknesses, they cannot do a very important task that needs to be done for this. That is, they lack the capability of doing what if simulation for policy testing. So our architecture that we post, it enables this very important feature, that is what if simulation for various kind of policy testing. So in the digital twin, since we are using digital twin, we can perform various analysis. Okay, if we have this base station and if we have this transmit power, if we choose this beamforming vector, what is going to be the throughput? If not, can we make it better, right? So other spectrum sharing systems, like existing spectrum sharing systems like TVW, SAS, and ProSAS, and zone management systems, they do not give us this feature to do vertical analysis, and that actually makes our programmable open spectrum twin different from all of these. So on the left-hand side in figure A, this is what our proposed post architecture looks like. So again, this is strictly based on ORAN architecture. So on the right-hand side, we have the centralized unit and the distributed unit, the CUDU. And these two blue blocks, these are on the bottom, we have the near real-time rig. On the top, we have the non-real-time rig, also known as the SMO framework. And in each of these blocks, notice that we have two digital twins. So one, in the near real-time, we have a local digital twin. And in the non-real-time rig, framework, we have the global digital twin. And also they have two sets of spectrum sensing and spectrum management applications. In the near real-time rig, we'll have to have XAPs. So we have the spectrum sensing XAP and the spectrum management XAP. And in the non-real-time rig, we have the spectrum sensing RAP and the spectrum management RAP. Also in the near real-time rig, we have a machine learning model repository and RAN database. So what is actually happening? If you follow the numbering, if you follow the steps, then I can walk you through this. What is happening here? What is actually happening here? So network telemetry data, for example, KPMs, right? They are exported from the open CUDU, right? And they are sent over to the sensing XAP and the spectrum management XAPs over the E2 interface. This is a standard open interface that is there, that is connecting that connects the OCUDU to the near real-time rig. Similarly, there is this O1 interface that is also another open standard interface in ORAN that connects the CUDU to the non-real-time rig. So so both are step ones, right? So as the data is being fetched from OCUDU to the near real-time rig, at the same time, data is being fetched over the O1 interface to the non-real-time rig. Okay, and in case of the absence of so I forgot to mention. So this entire system of RAP is called the ISSU and ISMU. So integrated spectrum sensing unit and integrated spectrum management unit. Also, we have this same integrated spectrum sensing unit and management unit for the near real-time rig as well. And see, there is this global DT. The main purpose of the global digital twin is to have a holistic view of the geographical area that this non-real-time rig is covering. So when I say holistic view, it has a bigger view or coverage. How many base stations are there, and where are the locations, how many buildings are there, right? And it is also able to generate synthetic data so that it is able to train the ML model repository to do spectrum forecasting. And then in number 3, so this data when you see the number 2, after all the data is fetched from the OCUDU to the rigs, then this data is utilized by the spectrum sensing RFs as well as the XFs to perform spectrum decisions. And then the global and the local digital twins, they exchange data to so when I say exchange data, so the local DT is, since it has to respect the near real-time rigs 10 millisecond to 1 second time frame, it is not simulating everything that the global DT is simulating. So global DT is actually able to generate policies, and it is just fetching that data from the global DT. And also the local DT has a smaller view of this entire world. So basically, POST ingests the contextual information such as deployment configuration, spectrum usage, and environmental and network parameters. And at the core of POST is the spectrum twin, which emulates the coexistence scenarios and enables what-if evaluation of potential spectrum sharing actions. And the power of POST is that it does not act, whatever spectrum sensing decisions are taken, it doesn't directly send that to the radio access network. It actually evaluates these candidate actions within itself, within the digital twin, and to predict the interference, and then it sends it back to the radio access network. And in this, in figure B, I'm just again showing the digital twin, right, that I showed before. So this digital twin, the foundational data is from the GIS data maps, and they are transformed or converted into pixelated maps so that it is easier for the digital twin to ingest. And then we do all sorts of state prediction, channel estimation, resource control, and all these things. And in post architecture, all this is modular. The network operator can just choose to include some module or not to include some module. So basically, we are proposing an open architecture, open spectrum sharing framework for the operators. So in summary, POST collects contextual information required for spectrum sharing, including base station deployment configuration, spectrum usage, environmental data, and WAN measurements. Then it does model training and update. And then it does what if evaluation using its global and local spectrum twins. And finally, it sends off the decision to the radio access network. And the decisions are such that the coexistence objectives are actually satisfied. We also did a test case of this post where we showed that actually our architecture actually works. Post actually works, and we implemented it like this. So we have this environment, right? We also have the weather information, and we all get all this information from Open Weather Map, Open Speed Map, and all these places. 5G information, 5G RAN information are transported to the near real-time link over the E2 interface. Also, various contexts and FSS interference information, they are transported to the Y1 interface. So over the Y1 interface to the digital twin. And from the RIG database, all this information, the RAN information, where the building locations are, and all this information is also sent to the digital twin to perform what-if analysis. And then the digital twin gives back feedback to the spectrum management XApp. So we already have a CAT3S algorithm that was developed by our lab. So we just chose to use that as our spectrum management XApp. And then we feed the control decision back to the digital twin to do what-if analysis. And once this is done, final optimized control decisions, that is transmit power, beamforming directions, etc., are sent back to the real world. So if we look at this first figure, and we're just showing preliminary results. So we are comparing our open architecture post with our with this CAT3S algorithm that is developed on top of Ascent to a static generic exclusion zone based scheme. Now, if you see across various antenna configurations, 4x4 antenna, 4x16 antenna array configurations, POST is always able to respect the threshold of -8.5 decibels, whereas static exclusion zone scheme is not able to do that. And this is for sunny. For rainy scenario, POST is again able to our digital twin, our POST architecture, the test case that we performed using our digital twin, that is Ascent, it is able to respect -12 dB. No, I'm sorry. It is able to respect this threshold for rainy season. Also, if you see carefully, the thresholds themselves are different because of various reasons. Because when it is rainy, because of rain attenuation and path loss changes, right? The threshold is much stricter because during that time the base stations need to transmit with different power figures, so that the threshold has to be stricter. But even then for rainy season, our architecture is actually able to respect that threshold. On the right-hand side, we are showing the aggregate downlink capacity, where again, post architecture, our approach actually outperforms a static exclusion zone based scheme across various antenna sizes in antenna array sizes for both sunny and rainy scenarios. Now I'm going to move on to fixed wireless access coexistence with fixed satellite service. Most commercial 5G fixed wireless access deployments operate in the sub-6 GHz spectrum. Because of exponential traffic demands that is expected or anticipated in 6G networks, there is interest in the FR3 range. However, this 12 GHz band, right? Dish network holds approximately 80% of the licenses. And because of fierce opposition from the incumbent, like Starlink, these efforts, the efforts of investigating spectrum sharing in this band these efforts have been stalled. But the good news is, despite this deadlock, the FCC has explicitly requested technical studies to be performed to see if specific terrestrial configurations, for example FWA, with controlled directionality, if they can coexist with satellite incumbents. So we present Ascent FWA, which is a site-specific coexistence framework, and it is tailored to the lower 12 gigahertz band. So on the right hand, we have this entire real world, as I showed before. However, since we're talking about fixed wireless access, we're not going to talk about standard UEs or user equipments or mobile phones. So instead of those, we have something called CPEs, or customer premises equipment, that is mounted on top of the roofs of the houses. So also there is an NGSO-FSS receiver, which is actually receiving signals from the satellite. However, since there are also macro base stations in the same band, there is an interfering link. So our job is to respect the interference threshold while also maximizing the macro base station of the 5G throughput. So we have assumed this real world where we have a fixed wireless access network composed of K macro base stations, N incumbents, and 2 NGSO-FSS receivers. This entire real world is then transported to the digital twin, where we have in the database, we take into account the locations of the macro base stations. These are the macro base stations, the locations of the NGSO-FSS receivers, the CPEs, the buildings, the distances between the base stations and the fixed satellite service FSS receivers, channel and the path loss models, and the antenna parameters. So on the left, I just showed in detail like the band where it is operates. Each macro base station employs a 4x4 planar array, and then the FSS receivers are mounted at 4.5 meters at the ground, which is a typical rooftop height. And the CPE, the customer premises equipment, they are distributed within each macro base stations 120 degrees. So 3 sectors, right? So 120 degree sector according to their positions. So this is what we have. So this is the real world, and then we have this digital twin, and we try to see through Ascent FWA if such a coexistence spectrum sharing scenario is possible. So we evaluate our proposed MBS NGSO FSS coexistence under various criteria. Let's look at this plot. So we have FSS receivers. We have FSS receivers, right? So we sort these FSS receivers from the cluster of the macro base stations. So when I say FSS receiver number 1, it is actually the nearest FSS receiver that is computed. The distance is computed from the cluster of the macro base stations. So FSS number 2 is further away from FSS number 1. and FSS receiver number 4 is the furthest away. These red dots, these are actually the aggregate interference to noise ratio in decibels. So intuitively, that this is what we should get as the receivers are further and further away from the macro base station cluster, the interference to noise ratio is decreasing. And again, this is the threshold that we have. And also, if we look at these box plots, we can see that for the first FSS receiver, FSS receiver, nearly all of the macro base stations, if they are turned on, they are not able to respect the threshold. But as we move on to the furthest FSS receiver, because it is further away because of the distance, we can see that almost more than 90% of the macro base stations, they are able to respect the threshold. Now, if we move on to this table, we can see that we have tested out the performance of this coexistence under 3 different criteria. The first criteria is we have considered 33 T-Mobile macro base stations, and this whole study has been done for the city of Raleigh in North Carolina. So we consider 33 macro base stations, and in the first criterion, we say that, okay, we are going to turn on all of those 33 macro base stations. And that is on this figure, all is represented by this blue line. So if we turn on all the 33 5G macro base stations, then none of them are able to, they are not able, for each FSS receiver, they are interfered. Because this is the threshold, right? So they are all above the threshold, all below the threshold. So they are all getting interfered. Now, if we move on to criteria number 2, what this is doing, we are saying that, okay, we are going to turn on only those macro base stations that have non-line of sight links with the FSS receivers. So you can see that for the furthest FSS FSS receiver number 4, this criterion number 2 is actually able to respect the threshold. And criterion number 3 is actually where we are saying that we are going to turn on those macro base stations that themselves respect the threshold. So if we do that, then yes, then each of the 4 FSS receivers, their thresholds are being respected with following this criterion number 3. So far, POST. So POST is programmable open spectrum twin, where we proposed an open framework which can be utilized by the network operators to host digital twin and do what if analysis. Then I talked about ASCENT FWA. So that is very specific to fixed wireless access in the lower 12 gigahertz. Now I'm going to talk about digital twin assisted cognitive spectrum sharing passive FSS receivers in the 12 gigahertz band, which is dubbed as DigiCap. So this is going to be a more generic kind of study where we are going to have macro base stations, UEs, number of users, as well as see if they can coexist. Our goal here is to not to coexist, not just to coexist, but also to improve or maximize the system throughput of the 5G base station, of the 5G network, along with respecting the thresholds. Also, when we are talking about passive systems such as FSS-ES, the problem is that they are passive receivers. They are not active, right? So there is a lack of active interference sensing reports. So passive systems, they neither transmit nor report interference, and conventional dynamic spectrum sharing strategies depend on this sensing report. So they fail. Also, as I mentioned before, there is a lack of context awareness. Existing DSS approaches typically employ static exclusion zone-based principles and worst-case propagation assumptions. And also there is a lack of intelligent algorithms. For example, current solutions, they rely on static thresholds, -5 dB, -15 dB, or fixed protection regions, which do not adapt to dynamic traffic. They do not adapt to environmental variations or beam level. They do not adapt to beam level transmission decisions. So we formulate the 6G FSS-ESS coexistence problem in the lower 12 GHz band. It is a constraint optimization problem, and it aims to maximize cellular performance while protecting passive incumbents. We develop a closed loop context-aware digital twin assisted base station control framework, enabling interference-aware decision-making without physical feedback. That is very important. There is no physical feedback from the passive receivers. And we use a realistic 12.2 to 12.7 gigahertz deployment scenario, FSS deployment scenario. And we demonstrate that DigiCam significantly outperforms the baseline, that is our own Cat3S framework and traditional exclusion zone based approaches. Again, this is on the right, we have this real world scenario. And from this real world, we take the static and dynamic context information, for example, the location of the users, the weather, and we store that in something called the context database. And from the context database, it moves on to the CDT, which is the context aware digital twin. And then from the CDT, it passes on these contexts are ingested by the digicam algorithms. We have developed two algorithms. One is a greedy heuristic approach, and the other is a recursive deep reinforcement learning RDRL approach. And then after doing what-if analysis in the CDT, the macro base station control parameters are then finally sent to the real network. So this is the DigiCam framework that we have designed. So the real world, and for us, the real world is we are getting all the real world information from OpenCell ID, where we get the macro base station locations. We also use the OpenStreetMap for the locations of various buildings, FSS-ES, and OpenWeather for weather, like whether it is sunny or rainy, and various operator telemetry. And all this information are stored in the context database. So this actually creates the static and dynamic context repository. And then it moves on to the CDT, or the context-aware digital twin. So these are some of the features of our context-aware digital twin, features as well as capabilities. So it is able to model the macro base station antenna pattern very accurately. It is able to model the antenna FSS receiver antenna pattern very accurately. It is able to model the line of sight and non-line of sight path loss and weathers. It can do resource block, RV scheduling and slicing, and it can also model interference. It can also model interference equations. All this information is then given or handed off to the two macro base station control algorithms. The first one is the greedy algorithm that we are using, and the second one is the RDRL algorithm. So here the problem that we have is it is NP hard and it is sequential and it is constrained, right? So RDRL is suitable because it is able to actually handle large action spaces. It all works well in dynamic environments, and it can incorporate constraints using Lagrangian relaxation, and it can learn directly from digital twin. But on the other hand, greedy algorithm, it makes a step-by-step decision, right? Basically, at each step, it picks the option that gives the best immediate improvement. It checks the interference using digital twin before activating a macro base station, and it actually does not think about the future. So that is the difference. So that's our RDL is able to predict the future, whereas greedy, as the name suggests, it greedily selects the best immediate improvement. We are talking about our CDT, right? Context our digital twin. So we validated our CDT with ray tracing using NVIDIA Sionna. So for every macro base station, we found out that our CDT, the interference to noise level that our CDT is able to achieve is very, very close to what Sionna is able to do. However, if you look at the entire simulation time for Sionna, including the experimental setup as well as the interference analysis, it is much, much, much longer than what CDT is able to give us. So we can say that our CDT is almost as good as the real world, which is obtained through Sionna. Yet we are able to satisfy the near real-time time constant of ORAN, or the non-real-time, or the near real-time rate. So let us look at some results that we get from our DigiCam framework, right? In the first one, for various rain attenuation, like low rain, where it is 8 millimeters per hour, medium rain, and heavy rain, as well as for sunny, for various weather scenarios, we are trying to see the aggregate interference to noise ratio that is given by DigiCam, as well as our baselines. Two baseline is the Cat3s and the exclusion zone based principle. And these are also based for various, not various, two different FSS Earth station pointing angles. So these are these big antennas, right? They point at various angles because they're tracking the satellite. So we chose 20-degree and 40-degree pointing angles. One thing that is clearly understandable from this figure is that you cannot see these two lines for these plots. That means that various like these pointing angles are not very significant because of a few reasons. The first reason is these FSS ES, these Earth stations, they're pointing up, whereas the 5G macro base stations, they are pointing they have a 10-degree down tilt. So even though the pointing angle changes, there is no real difference. However, the difference is that if we are looking at the baseline exclusion zone based principle, for whether be it sunny, whether be it rainy, it is not able to satisfy the threshold at all. However, the Cat3s is our second baseline Cat3s algorithm. It is able to satisfy the sunny threshold. However, it is not able to satisfy the heavy rain threshold. I mean, the threshold for heavy rain, right? I mean, rainy weather threshold. But our DigiCam, both greedy and RDRL, they are able to satisfy the aggregate interference to noise ratio threshold for sunny weather and rainy weather, whether it is low rain, medium rain, or heavy rain. On the right-hand side, we have plotted how many base stations or how many macro base stations our algorithms are activating, satisfying the threshold for sunny and rainy weather. Okay. Again, we have plotted for two different FSSES pointing angles. However, they do not make any difference. But we can see that the two baselines, exclusion zone based principle, it is not able to activate any, well, not a significant number of macro base station because it is static. But if we look at RDRL, DigiCam RDRL and DigiCam greedy, it is able to activate a lot more macro base stations. Specifically for sunny weather, DigiCam RDR, it is able to activate more than 80% of the macro base stations compared to exclusion zone. All right. If we look at the data traffic, right, we see that the baselines, the Cat3s, and the Cat3s, it is actually not able to activate. It is not able, whatever is the data traffic, right? Like look at this Cat3s and DigiCam. You see only single lines. But we are plotting this data for high traffic, medium traffic, and low traffic. So this is very clear that if we are using Cat3s or our DigiCam greedy-based algorithm, it is not aware of the traffic. But if we are plotting RDRL for high traffic and medium traffic and low traffic scenarios, it is able to activate different number of base stations. If it is high traffic, it is able to activate higher number of base stations, right? And for various antenna patterns, 4x4, 4x16, 16x16, for both sunny and rainy weather, again, Digicam RDRL is able to give us higher spectral efficiency in bits per second per hertz. Now we're going to move on to something completely different. This is the lunar digital twin that we are working on right now. So this is the Earth and the Moon, and the space between the Earth and the Moon is called the cislunar space. Okay. And around the Earth, we have the LEO, the GEO satellites, the intersatellite links, and similarly around the Moon, we have the lunar small sat network. And then between the two types of satellites, the Earth satellite and the lunar satellite, there is this interplanetary satellite link. So our LDT serves as a model of lunar communication networks that supports the NASA's Artemis scan and commercial space initiatives. It provides a valuable commercial resource for space-related business, and our LDT addresses key market needs as it is outlined in NASA's SABRE subtopic. So the NASA Glenn Research Center, GRC, in Ohio, they have their own emulation and modeling testbed, hardware in the loop testbed that they call GEM. So their GEM, the hardware in the loop testbed, it is able to do the following things, right? So it is a ray tracing derived lunar channel model, RFSIM. They use ANSYS RF channel modulator that provides ray tracing based channel simulations, and then it compresses them to 48 tap impulse response using emulator called PropSim. I mean, we all know about PropSim. And it runs real 3GPP waveforms using USRP and SRS band through the emulated channel and measures real physical layer metrics, for example, block error rate, MCS, data rate, and all these things. So on the right-hand side, we have this sample of lunar surface elevation map that they use to do all this, do the hardware in the loop testing. So that is GEM, right? That is an emulator. However, our LDT, it is a software-only simulation framework that uses NS3 and custom propagation models. It is able to read any arbitrary geometries from the configuration files that we are able to provide. It computes path loss, SINR interference capacity. It can directly integrate the 5G NR stack inside NS3 using the 5G LAN and all these things. And it has a Python GUI that can be used to modify the topology and parameters. And it is the most important thing is that it is scalable to any number of UEs. By the UEs, I mean like number of astronauts, rovers, and all these things, any number of G-node bees or satellites on the lunar surface. So in short, our LDT explores network level behavior and it does not explore hardware level radio behavior. So the question could be, are LDT and GEM, are they redundant? They are not. Actually, they are complementary. So GEM actually gives us the ground truth radio behavior, whereas LDT gives us network scale performance evaluation. And these are the capabilities of GEM and LDT. So they do not share the capabilities. So GEM is good in doing real RF hardware via PropSim, whereas LDT is a software and has scalability as its strength. I'll just go through this. Yeah, so these are some of the so this tool is still under development. We are still working on it and working hard towards getting phase 2 proposal grant. So here is, if you look at the GUI, you can put in any number of like parameters, like where do you want to put the terrain plan? You can just browse it and put it and import it there. What is the base station height? How many G-node Bs you can add G-node Bs on the lunar surface. You can specify, give the coordinates and see where you want to place this G-node Bs. where do we want to place the UVs, how many UVs we want to put in the on the lunar surface. So basically, our idea is to do what if analysis on the lunar surface. And then it is able to give us a 3D visualization as well as a 2D visualization. For example, there are astronauts here, there is a rover, then there is this base station, and how they are we have also implemented mobility model where we are able to show that the astronauts and the rovers, they're moving around, and in real time we are able to show the link quality, the SINR, these things are changing. So this is a whole rounded tool. So but the limitation right now is that we have only been able to do the lunar side of things, but we promise that we'll be doing the whole closed loop, the Earth and Moon side of things. So we are working on the Earth, I mean the cislunar space and the Earth side as well. So in conclusion, what I discussed is that I first talked about ORAN, the open framework, the Open Radio Access Network. And then I talked about the kind of flexibility our architecture, spectrum, our digital twin architecture post brings. Then I showed preliminary results about ascent fixed wireless access. And then I talked about Digicam, which is a framework where UEs, the 5G, 6G network, the UEs, they're able to coexist, and also able to maximize their throughput while respecting the threshold, the interference threshold of the FSS FSS Earth Station receivers. And I also gave a sneak peek on the lunar digital twin that we have been working on. And this concludes my talk. Thank you, and I can take questions.
And thanks, Ananta. Yeah, it was a great talk. I learned a lot of things. So we have a question and we are running out of time. So I will just quickly ask you that question. And I have one question from my side. So the question is from Anik, that from the perspective of wireless communication and security, what are the research problems, challenges in implementing 5G or 6G on the moon?
The first challenge is that we do not really have a realistic channel model that is going to work. We have channel models that work on the Earth, but lunar atmosphere is completely different. Like Earth, it doesn't have a thick atmosphere. There is also something called lunar dust. So because of all these things, we are not yet able to have a very accurate channel model. So that is the um, first challenge, the biggest challenge. And because NASA doesn't want to invent new communication protocols or technology, it is trying to see if the existing, with minimal modification to the channel models, if we can port our existing 3GPP technology to the moon directly, because for the future Artemis missions.
Okay, thank you. Anyone else having question, you can directly ask. And so the question I have, so you showed many of the digital twin based work, right? So the digital twin and the physical twin, they're kind of working together in synergy. So how, like, where are you envisioning to deploy the digital twin model, suppose? Is it in the cloud?
This is what we are going to be working on in the future. So we are looking into see, I showed that our CDT, if you remember the context of a digital twin, it is able to respect the time of the near real-time rig. So then it makes sense that we're going to use OSC rig or flex rigs or something like that to deploy and see in the real network how we can you actually utilize the digital twin. So yeah, we're going to looking to deploy it in using a real rig, RAN intelligent controller.
I see. So
Did it answer the question? Oh.
So that would be in the cloud?
If you look at POST, right? POST is a framework that we developed. Digicam is something else. So we are going to see if we can take Digicam, this entire thing, and implement it in POST.
I see. Okay. Yeah. Got it. Thank you so much.
Thank you.
Okay, thanks. Because we are running out of time, so thank you. It was a great talk, Santo.
Thank you. Thank you for the opportunity.
And so I'll stop the recording now.